is volume by washers. If you're good with volume by discs, then this will build off of that. If you're not good with volume by discs, you should come in because this is going to make things even a little more complicated. Let's go back to Algebra 1. First and foremost, either one of these, when you found a washer, you did that the volume of that washer is area of the base times the height, but the area of the base, because the area of the base was a missing circle in the middle kind of thing, you did it by taking that big circle and subtracting away the little circle, yeah? So you get something like pi big R squared minus pi little r squared times the height, okay? That's the idea of the day, but in calculus, you're going to add many, really little thin washers, and so it'll look more like pi and the sum of many r squareds minus r squared. You factor out the pi, and instead just focus on integrating the r squared minus r squared, and the height is either a dx or a dy, depending on how it's revolved, right? So that's what you're going to see. Now let's talk about a problem and what it looks like. Say you looked at this region and you revolved it around the x-axis. Now rather than get a completely solid situation, you're going to have a reflection. When this goes out through the board, this region comes out through the board and down, reflects down here, you would get a 3D figure like that, but with a big kind of funnel in the middle that's missing, yay? All right, now then, think of, I could draw lots of slices, but let's just draw what one slice would look like. If I did this one slice and revolved that one line around the axis, it would make a very thin washer. You've got a little bit of hole in the middle, and the hole in the middle comes from the fact that the curve doesn't go right up against the axis. Because the curve doesn't go right up against the axis, you get a little gap, and when that gap is revolved, you get a hole in the middle. Now this is what a washer problem will look like. When the region is not right up against the axis, a hole is made in the middle of the discs. And so we use washer. Alright, we got to take away that part that's not really there. So if we take the general idea of pi, we're trying to find the area of this disc, right? Because volume is area of the base times the height. Now we said the area of that base is pi big R squared minus pi little r squared times the height. That's the big idea of the day. The question then is in the details. Big R. Big R is the distance from the center all the way to the furthermost point, the R of the bigger circle. Here then, here's the center of the circle, and big R is all, that choice for color. Big R is all the way out from the center to there. What's big R for that disc? How big is that radius? 4, okay. Now the question is it always 4, or would different slices vary? Say I looked at this slice up here. If I did that slice and revolved it, the gap inside, the part that's missing, is really, really big. That washer is more like that kind of situation. But that said, what is big R for that next one? Is it still 4? Yeah, big R is always the same upper and always the same lower. The big R is always goes to 4 to the center, which is always 0. So this is always 4. So it'll be big R squared, 4 squared. Now little r, a little more going on here. Little r represents the radius of the gap, or the circle that's being removed, that we don't want to include because it's not part of the volume. Now, here's little r, and here's little r, and here's little r. Now little r, it seems like it's not always the same like the big R is. Little r seems like it's a value that's getting bigger and bigger. So what do we call little r? Yeah, it's the function. Okay, little r is the function. And so in this case, x squared. Now that's still little r squared, so it's x squared squared. What about the height? The height is how thick that disk is. And the thickness of the disk is not very thick at all. What is the height? Dx or dy? It's dx, okay? It's a thickness this way. It's a small change. When I talk about the thickness or the height, it goes this way. So it's a small change. Horizontally, it's dx. What about the limits of integration? If it's x, then I need x limits of integration. What are the limits of integration? 0 to 2 or 4? 2. Okay. All right. So the volume of this, then, we could use a calculator or do this by hand. Let's do this one by hand. What's the antiderivative of 16? 16x, and the antiderivative of x squared squared? X to the 5th over 5. X squared squared is x to the 4th. So antiderivative of x to the 4th is x to the 5th over 5. I'm getting something like pi times 32 minus 32 fifths minus zeros. Common denominator is fifths. What's 32 times 5? I guess we could just do 4 fifths. 32 minus 1 fifth of 32 is 4 fifths of 32. But either way, what's 32 times 5? 160 minus 32 is 128 pi over 5. You follow? Okay. Let's. All right. This one, I'm going to help you get a graph or picture of the area, then you're going to do the calculus. Right. So if we were to graph this, log base 2 of x. What's the basic shape of log? Yeah. Okay. Give me, where does it have a vertical asymptote? At the axis, y-axis. Give me a point on log base 2 of x. The x-intercept preferably to start with. The x-intercept is at 1, 0. What's the next good point? Log base 2 of what is nice? Log base 2 of 2 is 1. Log base 2 of 4 is 2. Log base 2 of, what's the next good value? 8 is 3. Okay, so log is just the inverse of exponentials. So it looks something like that. All right. Y equals 1. Is that a horizontal line or a vertical line? I know because it's y equals, it feels vertical, but it's really horizontal. And what about x equals 8? Horizontal or vertical? Vertical. All right, so the region enclosed is this one right there. Okay, now I'm revolving that around the x-axis. So here's my axis of revolution. So if I draw a reflection, now I love the 3D figure revolved, and it looks cool. But really, if you really want to help yourself with the calculus, draw a single slice revolved, so that your graph doesn't get too busy. We're getting lots and lots and lots of this like that. Now again, this is that case of today where the region doesn't abut or isn't adjacent to the axis of revolution. When there's a gap between the region and the axis, then that gap revolved makes a gap in the 3D figure and therefore a washer. Try from there. You may use your calculator to evaluate the integral, but first set the integral up. On the AP test, the most common mistake on this type of question is forgetting the pi. And that's will be off by factor of pi. Type it in right away. Don't think, oh, I'll do it later. I should do this unnecessary. Let's see. Base 2 x squared minus. And my answer is, what's your answer? Shut it out. 3? Surely not 3. What'd you get? Shut it out. Come on. You got a negative. You're definitely wrong. What'd you get? Give me your answer. 7? 20? Just shout out your answer. It's okay if you want. Just give me
83. Negative 82.
negative. What'd you say? 20? What? 80?
83.
80. I got 80-ish. 80-ish. Okay, so let's go here. Pi is pi. Thank you. Oops. Pi is pi, obviously. And so here we go. We need to identify big R. What's big R? It is the log, it's the function and squared. So it should be log base 2 of x.
Yeah, that's what you said.
I didn't say that.
Yes, you did. Oh, literally.
On the previous problem?
Yeah.
That was on the previous problem. This is a different problem.
It's different.
You think it's always the same?
Yes. You
That's ridiculous.
you said the little r is always the function.
No, in this problem, the r is the function. Why would it always be the function? That's ridiculous. That's crazy. You're just making stuff up. Okay? No, no, no. If I said this is always the function, then it would be for up here. Write this in. For this problem. Yeah, sorry. You can't follow a recipe for every problem. You have to think each time. Sorry. This then, it is not the big R. If you look at each slice, isn't big R always going to top out at the function? Yeah? Okay, so here's the upper to big R. The upper is always the function. The lower is always 0. So big R is the function. Square. Check. Little r. Little radius is, I'm talking the radius of the inner circle. Here's little radius. Here's little radius. Here's little radius. Little radius looks like it's always 1 squared, if you like. dx or dy? Dx. Limits of integration then? From 2 to 8. If you're good, your calculator then, log is in here if you like. In the subcategory, the sub-function menu next to the 9, there's the log function right there. If you slap that in with parentheses carefully, a lot of parentheses mistakes here. You got to be very careful with the parentheses. It is 80.103. All right? So, that's why we're practicing. Yay, good stuff. Okay, so the moral of that story is that big R and the little r are going to be problem by problem cases. Let's talk about y, shall we? Same region, but this time I'm going to draw it with lots of room on the left to draw because I'm about to rotate it around the y-axis. So here's that same region that we just talked about, formed by the log graph and the y equals 1 and the x equals 8. This time, though, around the y-axis, so the reflection would go this way. Now, just like in disks, when it's around the x-axis, we use x. And when it's around the y-axis, we use y. Well, in this case, then, we'll use y. If we revolve around the y-axis, then the slice goes this way. Okay? So if you draw a slice this way or this way, and its reflection, and then connect the inner, then you're looking at a case like that. There's the really thin pipe. It's lots of those little washers stacked on top of each other. Now, volume is pi big R squared minus little r squared times the height. So I need to find what's big R squared, what's little r squared, and the height. What is the height? Dx or dy? dy. All right. Big R. Big R is from the center of the circle to the outside of the circle. In that case, it looks like big R is what? 8. Is big R always 8 at every slice? Or is it varying? Is this right-sided? Constant, always 8, or varying? Constantly 8. Big R is always 8 in this case. Little r is the radius of the missing hole. Is little r constant or varying? Varying. Okay, right minus left. The right side seems to be the curve. So the function. But the function needs to be put in y terms. And so if we put the function in y terms, what is this in y terms? X equals 2 to the y. So big R It's the curve, but in y terms, so it's 2 to the y quantity squared. Do you remember if you had to graph this by, or integrate this by hand, how to integrate that well? The key is to change it to 2 to the 2y, or 2 squared to the y, or 4 to the y is the easier way to integrate that. You don't want to get into u sub with exponential. What are the limits of integration? Is it still 2 to 8? No, these need to be y values, so 1 to 3. Okay, you put that in, integrate that, and call it good. Try the next one on your own then, please. Use your calculator to evaluate. You're ready to give me an answer. I didn't do it is not acceptable. Yes. All right. Do you have an answer for me? Go. Okay. 194. 145. 126. 145. 145. Somebody in here? 127. In there in the middle, somebody. Give me. That's for you, 140. 145. It is 145. Ish. Okay, so let's see here. First of all, your outer R it goes from this axis of revolution, which is the x-axis, out to this point, but it looks like that every time is varying. So is outer r a constant or a function? It's the function. It's the function in y terms. So what is big R? Y squared. Little r is the radius of the inside donut. And the radius of the inside of the donut is always 1. It's always 1y. And then the limits of integration, are they from 1 to 3 or 1 to 9? What are the limits of integration? 1 to 3 are the y values. That's where you get an answer of 145. And if you divide that by a matrix to see this. If you got 46-ish, you might have forgotten the pi. This should be 145 point something. Okay. Let's go on to slight variations on the theme. Let's go with the area enclosed by that same region. Actually, but this time x equals 1. So here's the graph of the square root. Here's x equal 1. And here's x equal 3. This time, the difference is that I'm using x equal 1 and x equal 3. So this is the region here, yeah? If I revolve that around the y-axis, you have to be careful because you're going to get two different situations. Would you draw me? Oh, that's the most terrible reflection. Would you give me two slices? One down here, and then one up here where the curve is happening. In the lower region, the outer R is the right edge 3, yeah? And the inner R is line 1. In every washer I drew up until this point would always look just like that. In other words, it would look like a cylinder with no variation to it. But once you get to the top part, then you're starting to get a little different situation in the gap. You're starting to get a wider and wider gap in the middle, so a bigger and bigger little r. Because you have two different regions, then you need two integrals. Will I be using dx or dy here? If I'm around the y-axis, it's dy, yeah? Okay, so the lower region. I'll come to the limits in a second. Actually, let's go to the limits now. When does that lower region start and stop y stop? 0 to 1, okay? Now for that lower region, big R is here. What is big R? 3. And it's going to be 3 the whole time because the right edge is always the same. It's not changing. The axis of revolution is always the same. So big R is always 3. What about little r in that lower region of the graph? It's 1 every time. This is 1, this is 1, this is 1, always 1. Now when we get to the upper region where the curve starts to take effect, things will change. What about big R? Is big R tied to the curve now, or is big R still 3? It's still 3. But now little r is starting to grow. It's tied to more like going all the way to the curve, yeah? So it's little r. Y squared. And what are the limits of integration for the second region? 1 for x, 1 for the lower limit. That's the easy part. What's the other limit? Root 3, yeah, root 3. If you put in an x of 3, you go to a y of root 3, and then you close the region. All right. Last then is how to do this with the calculator, which is a pretty common calculator question. Would you get out a calculator if you don't already have one out? And put those two functions in, please. 4 parentheses sine of x squared. And what was the other one? X minus 1 Okay, so you have a region enclosed there. I might type my window a little bit. Okay, something like that, yeah? How are we doing? Now we're going to take that region and revolve it around the x-axis. So let's get a rough sketch. You've got a parabola and some other curve here, and you're revolving it around the x-axis. Now if I take lots of disks here, you can see that there are regions where there's a gap, yeah? So it's a washer case. Sound cool? Actually, go ahead and do this on your own. What do you reckon we're going to need to do? After we sketch it, what are you going to do next in your calculator? Somebody shout it out. Help us out, please. Store the values. Store the intersections. Well, you need the x's or the y's if you're going to go around the x-axis, then what's our variable of integration? Yes, so you should be storing the x values of the intersections. Here, let's call the left one A and the right one B. You need to record those to 3 decimals in your work. It's way too small. I got a left intersection of 0.337. How about you? And lower upper value of 2.380. Okay. All right, so we have our intersection points stored. 2.380. Bring this up to the side for a second. Okay, so we know that this is the shell of the problem. We're talking washers, so difference of squares. dx's are height of our washers. What is big R? Big R's here, or here, or here. It looks like big R is always a point on sun. And you may call it f of x to save yourself time. And little r. Now little r is here, or here, or here. What's little r? G of x. Now we just need to put that into our calculator without messing it up, and we're home free. F is F1, G is F2, okay.
Good morning, Devlin Jaguars. Please rise for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
All students, if you missed course selection for next year, please make an appointment to see your counselor.
Musical costume crew. We will be meeting after school all week in the drama room. Please let Miss Ann know if you can't be there.
Please check the lost and found tables in the main lobby to see if you have anything there. Items not claimed will be donated.
There are flyers in the main office for discounted nugget tickets. If you're interested in going to the game, please stop in the office and get one.
Come out to the Chipotle on 317 East Southwest Wadsworth and Lake West on Tuesday, February 5th between 4 and 8 to support your Devil and baseball team. Remember to grab a flyer from around the school or just tell them you're with Devil and baseball.
Students who participate in
You
the
have 53.998.
girls and for others that are interested in STEM, GE invites you to join their first Get to College Information Week this Friday during 7 o'clock.
Some of you turned in
To interact with engineers
79 already.
Colorado School of Life.
Do you have any questions I need to put up?
During 7 hours throughout the semester. It's open for girls that are
Actually,
grades 7 through 12.
If you have questions on 80 you want me to put up in line, shall remember to do that. 79, what else? What on 79?
The AP Chemistry pre-test for freshmen interested in AP Chemistry will be on Wednesday during
23 on 80.
Sign up for 7th hour on Wednesday with your science teacher to take the test.
By the way, you can always come in 7th hour and ask too. You don't have to. Just copy what I put there.
So it's just what you do.
80's due today.
Girls Chemistry.
That's on 80.
There will be an interest meeting today during 7th hour in the auditorium. All girls planning to participate, please come to the meeting.
Did somebody say 16?
February scholars of the month are as follows. Elizabeth Hatcher has been nominated for the Teen High Foreign Language Scholar for her commitment and continued success.
Is this on 79?
Elizabeth not only goes above and beyond work that is asked of her, but has a true interest in curiosity expansion. Whether it is asking thoughtful and creative questions, helping her peers, or committing herself to the only advantage she always preserves and makes perseveres and makes the class more enjoyable for everyone.
Mateo Newman is an outstanding Spanish 3 student. He is extremely curious about all aspects of the language and cultures that we study, and no detail escapes his attention. He is unafraid to ask questions to be certain that he fully understands all class material and readily participates both in English and in Spanish. His demeanor has a large impact on the classroom, leading to an open and fun environment.
Eva Benyon is an exceptional French 1 student. Eva excels in all aspects of French. She easily understands spoken French and responds quickly and appropriately to questions. Eva's conduct is exemplary. She is kind and willing to help others. Notably, she is a wit with numbers in French, and as a classroom, she is known to use time and French faster.
Finn Rappaport has been an outstanding Spanish lesson here. He is a consistent participator in his competition. His energy, humor, and enthusiasm are contagious. He is a direct friend of the Spanish language and asks
Yes, I do.
He has a remarkable ability to communicate with others.
The boys play their last home basketball game of the regular season this Friday against Weaver High School. This past Home Conference, we celebrate our seniors on defense. Save Jeff Cox will be on at halftime. Go Panthers. The boys are at Liverpool High School this Wednesday. The varsity starts at 7 p.m. Also, don't forget to Dr. Jones tonight as the girls take on Everton at 7. That's all your announcements. Have a great day.
I have some papers to hand back over to my Esther, oh, Esther. You're welcome, have a great day. I will have those.
Mr. McNichol.
Yes. Yes. So you can get their wire call us. Hey, there he is. Ooh. Nice game. Good luck tonight. Welcome. Okay.